All right, so in this example, same directions. Find the radius and interval of convergence. So looking at this, I know that the center of my interval of convergence is 2. So it's going to converge there for sure. Now we got to see, does it converge for some more x's, or does it converge for all x's, or just that x? To do that, we're going to look at that ratio test. So I'll say the limit as n goes to infinity of the n plus 1 term over the a sub n term. That's equal to the limit as n goes to infinity. I'm going to plug that in. So I'm going to plug in n plus 1. It'll be 3 times x minus 2 to the n plus 1 over the nth term. So now I'm going to rewrite, kind of see if I can cross some stuff out. So the 3's, I'm going to cancel out the 3's. But the x minus 2 to the n, I can write that as x minus 2 to the n times x minus 2 over x minus 2 to the n in the absolute value. So what we're basically doing, I didn't say on the last one, but all those numbers that are in between 2 and 8, they converge absolutely for that. So in the interval of convergence, it converges absolutely. Then on the edges, it could converge absolutely, conditionally, or it could diverge. Okay, so this cancels. So the limit as n goes to infinity of x minus 2, well, where are the n's are all canceled, right? So when I get that, when they're like the n's just kind of cancel out, they give us 1 or whatever, I know the limit as n goes to infinity, it's not going to be 0. It's not infinity. So I'm going to see where this converges when the absolute value of x minus 2 is less than 1. So add 2, 1. So this thing converges absolutely for all the numbers in between 1 and 3. And I want to kind of demonstrate that on this one. So let's take some time and look at it. If I plug in a number between 1 and 3, it's going to converge absolutely, meaning it doesn't need the alternating series part to converge. So if I plugged in, let's say, let's plug in 2.5. If x is 2.5, I would get the series 3 times 2.5 minus 2 to the nth power, which is just an geometric series with r less than 1, so this converges. And the absolute value that converges, so I mean it converges absolutely. If I took a number like when x was 1.5, this would be 3 times 1.5 minus 2, which is equal to the series n equals 1, 3 times negative 0.5 to the n. Even though that is negative, it's still a geometric series. So if I took the absolute value of it, I would just get what I got before. So this converges absolutely. Any x value within, like not on the edges, but within there, converge absolutely. Now on the, oh, are you kidding? All went okay. All right, so let me write that one part down again. So I got x's in between 1 and 3. I tested when x was 2.5, it converged. When I tested 1.5, it converged. Let's just test for fun x equals 0.5. Notice it's not within our interval of convergence. So this thing is going to diverge, and let's just see why. This would be 0.5 minus 2 to the nth power. This is n equals 0 to infinity. This is a negative 1.5. So this is a geometric series where the absolute value of r is greater than 1. So it's an alternating series where the limit doesn't equal to, the limit of the terms doesn't equal 0. So this diverges. So it diverges by a geometric series test also. So that thing diverges. Any x value not within that interval of convergence will make it diverge. But we still need to test the endpoints. So we're going to test when x is 1 and when x is 3. Now on those points, it could converge conditionally, it could converge absolutely, or it could diverge. But all we really care about is if it converges or diverges. I don't really care about absolutely or conditionally just yet. All right, so n is equal to 0 to infinity, 3, okay, plug in 1, so that's what, -1 to the nth power. So that is a diverging, by the nth term test, it diverges. Or by geometric series test, it diverges. So I don't include that. I just leave it x greater than 1. If x is 3, I've got a series, 3 minus 3, so it'll be what, 1. And by the nth term test, that thing diverges also. So the interval of convergence is all the numbers in between 1 and 3, not including 1, not including 3. And the radius of convergence would be 1. All right. Let's do another one. Number 3, find the radius of the interval of convergence. So whenever I get like a series, a power series, and I've got x in there, I'm thinking, okay, they're going to ask me for what x values does this thing converge. So it wants to know the interval of convergence. So I'm going to set up my little ratio test thing. The limit as n goes to infinity of the a sub n plus 1 term. So it'd be n plus 2, because n plus 1 is n plus 2, over n plus 1 cubed times the reciprocal of that original thing. And now it's just some algebra. We got to kind of manipulate this to find out what the limit as n goes to infinity is. This would be x plus 1 to the n plus 1 times x plus 1 times n cubed all over n plus 1 cubed times x plus 2 n plus 1. All right, would I write something wrong somewhere? Oh, these should be x plus 1, so whoops. I'm sorry. Change all that. That's a 1. But this is x plus 2. That's x plus 2. That's x plus 2. Okay. So from here, this cancels with that. Nothing else really cancels, but I can evaluate the limit as n goes to infinity of n cubed over n plus 1 cubed times x plus 2. All right, so looking at the limit as n goes to infinity of this is just 1. So this is just equal to the absolute value of x plus 2. And I want to see, okay, for what would make it converge? The ratio test says this converges if the absolute value of a sub n plus 1 term over a sub n is less than 1. So I'm going to find that. Set that less than 1. So x plus 2 is in between 1 and -1. Subtract 2 from everywhere. Get -1, x, and -3. So there's your interval of convergence, but we need to test the endpoints. We need to test when x is -3 and when x is -1, because the series could still converge for those numbers. Those are just right at the edge. So I'm going to check when x is equal to -3. Plug in -3 for x. -3 plus 1 is -1. N plus 1 over n cubed. This is an alternate, or this is a p-series. But the alternating series test says it converges. Alternating series, the limit of the terms approaches 0. It's alternating. So alternating series test says this converges. So it means I'm going to include -3. Now, does it converge absolutely or conditionally? I don't really care. I know it converges. But if I wanted to, if I took away the negative, the alternating part, this would just be n is equal to 1, okay, 1 over n cubed, which is a p-series that converges. So it converges absolutely at -3. But I just care that it converges. When x is equal to -1, I have an infinite series, just 1 over n cubed. which is a p-series that just says converges. Oh, that's terrible. All right, so I include both of the edges this time. So the interval of convergence are all the numbers in between -3 and -1, including -3 and -1. And the radius of convergence would be 1. All right, let's keep going. Okay, let's see what else could happen here. Number 4 and number 5 are just like the special ones, the ones that kind of weird things happen. So I see dx, it says find the interval of convergence, find all the x's where that thing would converge. The center is 0, so I know it at least converges for 0, but it might converge for everything. All right, so let's say the limit as n goes to infinity of the n plus 1 term, so this would be 2n plus 1 factorial times x to the 2n plus 1 over n plus 1 factorial times the reciprocal, so the original a sub n term. All right, and this, let's manipulate this around a little bit. The top would be 2n plus 2 factorial right there. This would be x to the 2n plus 2. So if I see that, I want to write it like this so I can compare it to this. That would be rewritten as 2n plus 2 times 2n plus 1 times 2n factorial. X to the 2n plus 2, I want to write it like that, so it'd be x to the 2n times x squared times n factorial. Just write that all on top. The bottom, I keep it all the same. Actually no, I don't want to write it all the same, because I want to match it with this somehow. So I would write this as n plus 1 times n factorial, then times 2, then factorial, x to 2n. Okay. Now the fun part, canceling stuff out. That cancels, n factorial cancels. And I'm left with, I'm going to group the n terms together to maybe see it a little bit better. So I've got on top, the highest degree would be 4n squared plus ... times x squared, right? I'm just going to keep it like this because I'm lazy. 2n plus 2 times 2n plus 1 x squared over 2n plus 1. What is the limit as n goes to infinity? Well, the n's actually matter this time. They're not just canceling out and being 1. So the limit of that as n goes to infinity, it doesn't matter what x is, the top grows without bound. So this limit is infinity. So that means the terms are just getting bigger and bigger and bigger and bigger and bigger and bigger. So that means the only way this series will converge if this x is equal to 0. So it zeroes everything out. So it only converges for x is equal to 0, and that means the radius of convergence is 0 because there's no width to the interval, so just 0. All right, number 5. Okay, so I see the x power series, interval convergence, the limit as n goes to infinity. Solving this is equal to the limit as n goes to infinity of x to the 3n plus 3, because I plugged in n plus 1 for 3, or for n, and then n plus 1 factorial times n factorial over . Alright, when that happens, this cancels with this. That cancels, and I'm just left with a limit as n goes to infinity of x cubed, no n's on top, and just n plus 1 on the bottom. So as n grows infinitely larger, the limit of this is just going to be 0. So it doesn't matter what x is. As the terms get bigger, they're getting, like the limit is 0. So this thing converges for all x. The radius of convergence is infinity. All right, we're gonna ask a couple other questions. We're gonna make this video another part. So that's it for this one. Thanks for watching, and hopefully it helped. Bye.